Okay, today we're happy to have Ofri Telem visiting us all the way from Berkeley. He was Java's student at Cornell, and he's going to tell us about the exciting world of amplitudes for monopoles.
Thank you, and it's been a pleasure to work with you, John, on this project and on many other possible follow-ups for this. And this is something that I've spent a lot of the past year thinking about, and I think they're pretty exciting results here. So let us jump right in. So I always like to say that the motivation for this work is the fact that the on-shell program has been very successful in the past decade, 15 years. And this figure I stole from a review by Tzvi Bern et al., which talks about, among other things, double copy relations between different theories, which are things you can only so far, I think, see on shell. Maybe there's some progress to see it in a Lagrangian level, but the main point is, without getting into the details, that there's a different language to talk about scattering and other aspects of quantum field theory, which doesn't involve an action or a Lagrangian necessarily, and might shed deeper, more light about deeper physics questions. So the gist, like I said, is that you do quantum field theory without referring to an action. And just to give some examples of cutting edge results, so there are 6 gluon planar n equals 4 super Young Mills, amplitudes at 6 and 7 loops, non-renormalization and operator mixing in Smith, black hole binary dynamics, which even compete with the numerical relativity results for LIGO, cosmological bootstrap, massless amplitudes beyond polylogs, and many, many things I didn't include here and I'm not going to go into. And when I see this impressive list of results from the on-shell program, I always ask myself, is it that we can just do things faster, things we would have done with a million Feynman diagrams, can we just do them more easily? Are we basically saving computational power, or are we shedding light on deeper questions? And I think there are hints that we are, as a community, discovering deeper things about quantum field theory. First and foremost, um, through color kinematics duality and the double copy, which uncovers some relations, this meme of like gravity equals Yang-Mills squared and all the other relations you saw in the figure that you can see from an action point of view. And there's also a classical counterpart that maps out solutions to Yang-Mills and electromagnetism to gravity, classical solutions of gravity. There are other hints like dual conformal invariance that I think was discovered on shell and Plutohedra, and recently also the hard S-matrix. And I think what we investigated here is yet another example of some deeper understanding of QFT that can be described in an on-shell way. So why do we think that monopoles are this good, like, testing ground for the on-shell program? The answer is very simple, as John knows very well. Since the days of Dirac, there's no clear way to write a local and Lorentz-invariant Lagrangian for monopoles, abelian Dirac monopoles interacting with electric charges. So there was the Wigner approach, which is to write a non-local Lagrangian, and the complementary Zwanziger approach, which introduced a local Lagrangian. However, there's an explicit Lorentz violation at the level of the Lagrangian because there's an explicit direction there, which is effectively the direction of the Dirac string. Now, that Dirac string enters the propagator of the photon that would connect a monopole and a charge. So when you come to calculate amplitudes with this, it seems that you'll get amplitudes that are Lorentz violating. Now you could say that you don't care about this because you square the amplitude anyway, and if this Lorentz violation amounts to a phase, then you can just forget about it. But for example, when you include just one photon exchange, it doesn't seem like the Lorentz violation is exponentiated to a phase. So it looks like your cross-section will actually be Lorentz breaking. And this is something that Weinberg already noted in 1965. And this is linked to, of course, the paper that John and Chris wrote in 2019 about the Weinberg Paradox. And what they uncovered is that if you take some kind of unknown hard scattering, and you sum all soft corrections to that scattering, a charge-monopole scattering or dion-dion scattering, what happens is that the propagators of the photons exchanged between the charge and the monopole eventually exponentiate. And if we consider not exactly scattering, but a charge that moves along a closed trajectory in the presence of the monopole, this Lorentz violation actually becomes just an integer times 2 pi. So it drops out of the amplitude, and that's the linking number. So there's a hint that somehow Dirac quantization serves to eliminate the Lorentz breaking from the amplitude. But it's a little hard to see this in other contexts because you have to sum an infinite amount of non-perturbative. It's a non-perturbative process because E times G is an integer, so you have to sum infinite ladders of photons to see it. So maybe on shell you can do better. Okay, so it's an on-shell opportunity. There's no valid Lagrangian you can write, but the S-matrix seems to be completely consistent, local, and Lorentz-invariant. So the S-matrix is consistent, but it has to be special in some way. Otherwise, why wouldn't you be able to write a Lagrangian description? And our intuition is that it has something to do with Dirac quantization, because for a charge in a monopole pair, Q equals E times G. It's a half integer. We know other half integers in the case of the S-matrix. These are spins and helicities. But note that spins and helicities are usually associated with a single external particle in the S-matrix. However, in Q equals E times G, the E is of one particle and G is of the other. So there has to be some half integer quantum number which is associated with pairs of particles. And this is very different from what you see if you open Weinberg, where spins are associated with single particle representations. So that leads us to think about pairwise helicity. Good. Let's gain some intuition by looking at the classical and then the non-relativistic quantum counterparts for charge-monopole scattering. So first, let me define what I mean by a monopole. So in my mind, a monopole is just a Polyakov monopole, but we're zooming out of it so that we don't care about the non-abelian physics at the core. So for us, we're effectively looking at an EFT in which the monopole is just the Dirac monopole. And in terms of the topological structure, I always like to think about it in the Wu-Yang formalism. So you define the vector potential on two hemispheres, which you suit together on the equator. And in that construction, there's no Dirac string, and Dirac quantization just comes from the demand of consistency of showing the two hemisphere definition of the vector potential. So what happens if I put a monopole, a static classical monopole here, and a static charge here? J.J. Thomson already in 1904 did the calculation of calculating the angular momentum that's stored in the electromagnetic field that's sourced by these two static sources. And surprisingly, the answer is non-zero, and it's even distance independent. So this you can do using just Jackson E and M. You take the pointing vector in all space, and you cross it with a position vector, and you do some trivial manipulations, and you get that it's minus E times Z, G times R hat, which is the direction from the monopole to the charge. So there's this is pretty remarkable. Even classically, there's angular momentum in the system. The sources are static, and it's even independent of their distance. So one could be at a different galaxy, but you're integrating over all of space. So there's this irreducible contribution to the electromagnetic field. And this is also going to come into play when we consider the asymptotic states of the S-matrix. And just to comment here, in the quantum theory, angular momenta are quantized. So this is another way, um, written originally by Saha in 1936, of seeing Dirac quantization from the quantization of angular momentum. Any questions so far? All right, good. In the non-relativistic quantum theory, we just write the Hamiltonian for a charge in the presence of a monopole, which is sourcing a magnetic field. We are covariantly coupling the charge to the monopole, and we're using the two hemisphere formalism of Wu and Yang, in which on the two hemispheres, the vector potential is defined through this. And we see that the conserved angular momentum of the system is no longer just r cross the derivative, linear momentum, but actually there's an extra piece here, which is corresponds exactly to the classical contribution that we saw earlier. So the angular momentum of the system is modified and has an irreducible distance-independent magnetic contribution, which is also quantized. And finally, let me note that in the case of two dyons instead of a charge and a monopole, E times Z generalizes to E of the first times G of the second minus E of the second times G of the first one. And that's called the Zwanziger-Schwinger quantization condition. So what you want to do is, relativistically, we want to construct an S-matrix. Just to summarize what I said earlier, I'll give the main idea. If we were just working in a Lagrangian formalism, what we would have liked to do is to consider the scattering of a charge in a monopole and sum up all photon exchanges between the charge and the monopole. But this is inherently non-perturbative because E times G is half integer.
So sorry, could you go back for a second? I just wanted to. Sure. Could you just go back one slide? Yeah. Okay. Yeah. Go ahead. I'll think about my questions some more possibly. Okay.
Sure.
Yep. Thanks.
Okay. So we want to do relativistic scattering of a charge in a monopole, and if we wanted to do it the old way, we'd sum up all corrections to all orders because the scattering is inherently non-perturbative. The coupling between the photon and the monopole and the coupling between the photon and the charge, their product sums up to an integer. So if one is weak, the other is strongly coupled. So basically, there's no small parameter for the expansion. Moreover, because we know the non-relativistic quantum mechanics result, we know that the potential result of being able to sum up this whole ladder would mimic the fact that there's extra angular momentum encoded in the classical electromagnetic field sourced by our monopole and charge. So somehow there should be a way to just, instead of summing a non-perturbative ladder, redefining our Hilbert space in a way which kind of already integrates out the angular momentum contribution from the classical electromagnetic field that is sourced by the monopole and the charge. And that is what we do. We kind of coarse grain, we integrate out the classical field by redefining our Hilbert space and assigning this extra angular momentum, which really physically comes from the classical electromagnetic field, to pairs of dyons or charges and monopoles. And after redefining the Hilbert space, we'll see that the S-matrix constructed from this Hilbert space encapsulates exactly this extra contribution of the classical E and M to the quantum charge monopole scattering. So let's dive right into how to redefine our Hilbert space in our S-matrix. But first, okay, so that is the plan. We redefine our S-matrix, and then we write down rules for how to write down amplitudes, and then we have some results for 3 and 4 point amplitudes. So the first thing that I'll do is I'll give you a recap of how to define asymptotic states of the S-matrix, and that's the famous Wigner method of induced representations. Basically, the asymptotic states of our S-matrix are representations of the Poincaré group. But because the Poincaré group is non-compact, it's a little tedious to try to define representations for it. So what we do instead, we focus on the subgroup of it, the stabilizer of some reference momentum, which is M000 for a massive particle, or E00E for a massless particle. And then we look at the stabilizer of this momentum, all the Lorentz transformations that keep this momentum constant. We define particles as representations of these little groups, these subgroups of the Lorentz group which stabilize the reference momentum. And then for each arep of the little group, we can induce the representation or the transformation of under the full Lorentz group. And so that's how you usually do it. For the massive little group, you label the little group as SU2 and you label representations by spin. And for massless particles, the little group is actually the Euclidean group, but we only care about its U1 part. And the labels of the representations there, the charges, are just helicities. So particles, massive particles labeled by spin, massless by helicity. And usually when we go to multi-particle state, we shrug our shoulders and we just say, oh, these are tensor products of single particle states. And this is exactly what we're gonna modify in our construction. So following a very interesting paper by Zwanziger from 1972, which actually inspired this entire construction, we look at the multi-particle state for two dyons that are also scalars in terms of their single particle little group representations. Naively, you'd say that because we decide that these are scalars, the way the Lorentz group, Lorentz transformations are represented on the quantum state is just the lambda, the Lorentz transformation, acting separately on each momentum. And there's no overall phase because these are scalars. But if that were the case, and we took the classical, the non-relativistic or the classical limit of this construction, we would find that there's no extra angular momentum associated with anything in that problem. So there has to be some extra ingredient representing the contribution of the classical E&M field. So at first, what we do is we just postulate that there's an extra phase, and that extra phase involves a half integer, which is called pairwise helicity, times some little group phase. And that encapsulates the fact that there's extra angular momentum in the problem associating with a pair of particles, because this little group phase is associated with P1 and P2 of the two dyons. So this is the pairwise little group. And actually what we do is we don't just postulate it, we can define it by repeating the Wigner method of induced representations, but working with a two particle state instead of a single particle state. And that will give us a two dion state, which is more generic than just a tensor product of two single particle states. So let me tell you how this is done. You have two particles. You want to define the general multi-particle state for them. What you do is you go to the center of mass frame in which one particle is traveling upwards along the z direction and the other is traveling down. These are the two reference momenta that are defined here. PC is the center of mass momentum and E1, 2 are the energies on the center of mass frame. And now the little group is the stabilizer of both momenta. So you want all the Lorentz transformations that leave both K1 and K2 invariant. And it's easy to see that these are just rotations, U1 rotations around their common axis. And if these are U1 rotations, we can label the representations under this U1 by their charges, and their charges are the helicities Q12. Now at this point, Q12 has nothing to do with electric and magnetic charge, right? So I could give this entire talk and not give an interpretation of what this integer Q12 is. I have a completely consistent construction of the Hilbert space and later the S-matrix. But in order to put some physics into it, I will tell you that the construction with this Q12 actually mimics the situation for a charge in a monopole if you make the identification Q12 is E1G2 minus E2G1. So in short, I have two particle representations with an extra quantum number called pairwise helicity. It's half integer, and it's associated with a pair of particles rather than one particle. Any questions about this point? Okay, and the last thing to note is that these particles can be massive. So here there are M's, right? So we are used to thinking about massive particles as having an SU2 little group. And it's true that each one will have its own SU2 single particle little group. But on top of that, there's an extra little group associated with a pair of particles. And that little group is always a U1, as it should, because it's labeled by pairwise helicities, which are Dirac quantized. So this is the two particle situation that was constructed by Svansiger. Oh, right. So I told you how what the representations are under the little group are, and the next step is the Wigner step, where the little group representation induces a full representation under the Lorentz group. And the way that it's done is we define a canonical Lorentz transformation that takes us from a pair K1, K2 of reference momenta to our finite momenta P1 and P2. And now we do the usual Wigner trick, mimicking exactly the single particle step. And here, that transformation takes K1, K2 back to K1, K2, and this is why it's a little group rotation. And we know how the state is represented under the little group. So all in all, we have a recipe how to derive this little group phase, and the integer associated with it is just the pairwise helicity. This is how you define a two-diene state. Good. The generalization of it is automatic. This is a little bit of a long formula, but it basically contains almost the same information that we had in the two-particle state. So the most generic multi-particle state that you can define transforms under the Lorentz group in the following manner. The momenta get multiplied by lambda. Each particle has its own single particle phase, which can, single particle factor, which can either be a D matrix for massive particles or just a phase with a helicity in it. And in addition, we have all these pairwise quantum numbers, which go together with an overall phase, which is linked to all the pairs in the amplitude. So if we didn't have this pairwise part, our multi-particle state would have been just a direct product of single particle states. But this one links pairs. So it just means that physically, even when the particles are asymptotically separated, there is still something linking them. It's not an interaction, because it's not like we have some interaction at a distance, but still there's an irreducible angular momentum associated with asymptotically separated pairs. So this is just the right amount of non-locality that leads to the fact that you can't write the Lagrangian for this theory, and yet you can capture it by defining these new multi-particle states.
Can I ask a question?
Yep.
So you can certainly write down this ansatz, and phi is the same function that you had before.
Mm-hmm.
And the result is that this is a unitary representation of the Lorentz group. That's what's one way I can look at this.
Yep.
Okay.
Yeah, and we also have another paper in which we did the detailed formal construction of these multi-particle states. So that's its own paper. And actually, that's actually your question foreshadows that construction. But I actually think I'll leave it for the questions later, because I want to get to the more exciting physics, in my opinion. And then if we want to address the formal construction more later, I'd be happy to do it. Good. So we have generic multi-particle states. They transform.
Can I just ask again? I mean, so this is a representation right, but how do I know this is actually what describes multi-particle final states per monopoles? Is there some kind of test?
Yeah. So you can take the non-relativistic limit and see that you reproduce the non-relativistic scattering of charges and monopoles, which is what we did later, and you'll see in the talk. So for example, Kazama, Yang, and Goldhaber in 1977, they solved the Dirac equation for a charge in the presence of a background monopole. And in this case, the charge was a fermion. And they found the full amplitude by just solving a quantum mechanics scattering problem. And using our tools and our construction of the S-matrix, we were able to basically reproduce almost everything in the result.
But I mean, for more than 2 particles, is there a test of this for more than 2 particles?
Yeah, because I think what you can do is you can define the angular momentum operator acting on a pair of particles, and act on these quantum states, and you'll see that the existence of this extra phase exactly corresponds to the contribution of the electromagnetic field sourced by these pair of particle of charge and monopole to the electromagnetic field.
Yeah, I mean, I'm not doubting that it's correct for a pair. I'm wondering if it's really true that for 3 or more, you just sum over the pairs and include these phases. So
Right.
The fact that it's a unitary representation means that that could be the answer, but I'm wondering, why is it the answer? Why should I be convinced that it is the answer? The answer for real monopole scattering.
Right.
3
Good
or
question.
more particles.
Good question. So from the point of view of our construction, you couldn't have done the same thing and gotten helicities associated with triplets of particles or more pairings. And the reason for that is because in the construction itself, you looked at the stabilizer of 2 reference momenta. And you could say, what if I had 3 particles? I wanted to stabilize 3 momenta. Now, the answer is that you can't. So the pairwise little group can be represented non-trivially, but the 3 particle little group can only be represented as nothing. So there's no, you can't have triplet helicity. Or
sure, I understand that, but that's actually part of the reason I'm asking, is because I could see that there are plenty of ways to see that for 2 particles, this has got to be the answer. Mm-hmm. But for 3 or more, it seems a lot less clear to me. I don't know.
For 3, you can go to higher dimensions. In higher dimensions, then there would be a 3 particle helicity. So you can
that somehow doesn't sound like it's addressing the heart of the issue. I mean, I'm just wondering, I mean, it's why, I mean, why is it, is there some intuition? Is there some calculation that says that it's somehow only these pairwise helicities that matter? There isn't some other quantity that knows about all 3 particles simultaneously?
Let me try to answer, but I'm making it up on the spot, right? So let's now imagine for a second that each charge monopole pair is somehow a charge monopole pair for a different electromagnetism. In that case, you'd agree that it's just, the sum over all pairs, right? So I guess the difficulty arises when you say, what if I have a monopole and then 2 different charges charge under the same electromagnetism? Is there some triplet effect in that case? I guess classically you can just say it's a superposition, right? If I go classically to the Thomson calculation here, right? What if I had just another charge right here? Then by linearity, I could just say that the total J is just the sum of the J's from the pair of the first charge in the monopole and the second charge in the monopole. Do you agree with the classical argument?
I mean, the superposition principle doesn't seem to hold for 2 monopoles. Why does it hold for 3? I mean, this is an extra contribution to the angular momentum that comes from the interference. So actually, that's what I was expecting you to say, is that, but did you actually check this, that if you just have n monopoles, static monopoles, that the extra classical, that would be some evidence for this, right? That if you have 3 or more monopoles, that the extra angular momentum is a sum over pairs of this. Is that true?
Since we're talking about asymptotic states, they're infinitely far apart, so it's certainly true.
Okay, so let them take the limit where they're infinitely far apart. Is it true? Did you check?
We didn't check for the classical calculation for multiple monopoles, but I'm sure it's true. I mean, you just take the B in all of space is the sum of the B that's sourced by monopole A and by monopole B, right? So
I agree with the superposition principle, but I'm not sure how that gives you this result. Maybe I'm just being slow, but
I mean,
I don't want to stop you. So if
yeah,
no,
I think it's interesting.
Go and give your talk, but it's just not obvious to me.
Let's discuss it later. I think it is an interesting question, but I can't prove it to you, but I think it works. Okay, so we define multi-particle states, and we're one step away from defining the S-matrix. Of course, in the S-matrix, you have to define in and out states, and that we do kind of similar to how they're defined in Weinberg by looking at the Heisenberg picture. The one difference here is that there's actually an extra choice, because when I defined the multi-particle states here, I could have defined it with a minus sign in this overall phase, and the whole thing would be perfectly legal, a perfectly legal expression. So I have a choice of an overall sign in this phase. And a priori, I wouldn't know if there's a plus or a minus here, or even if there's a different choice of sign for in states and out states. But actually, by considering the non-quantum but relativistic limit, we can fix the fact that there's a plus sign here for in states and a minus sign for out states. And that's linked to the fact that when we calculated this angular momentum, it was E times G times R hat, which actually is either parallel or anti-parallel to the direction of the momentum for in and out states. So that leads to a plus and minus in the formula for the relativistic angular momentum that comes from the charge monopole. And when you trace it back, you see that it leads to a choice of a plus and a minus for the in and out states in here. The plus and minus is important because that will lead to the helicity flip for fermion-monopole scattering. So to summarize, the S-matrix is just an in-state dotted with an out-state, and the way it transforms under Lorentz transformations, it gets all the single particle little group matrices that you think it does, plus an extra phase here, which is the sum over all the pairwise helicities times pairwise phases for the in-state and the out-state. And the plus sign here is because of the plus minus choice for the in and out state. One thing that you immediately see is that this S-matrix manifestly violates crossing symmetry, because there's some privileged definition of an in-state and an out-state. You don't have a Qij for a charge in the in-state and a monopole in the out-state, for example. So that's inherent crossing symmetry violation, which you also see in other constructions of charge monopole scattering. Good. So we defined multi-particle states with this extra phase. We defined our S-matrix. And now what we would like to do is we would like to come up with the little group formalism that will tell us how to construct amplitudes that have manifestly have this transformation rule. So what we would like to do is define new spinor-helicity variables that are associated with pairs of particles in our amplitude. They transform with an extra pairwise little group phase, and then we would like to use them as an extra Lego block to build amplitudes. So now our amplitudes will be a bunch of spinor-helicity variables for massive particles, for massless particles, and also pairwise ones. And I match them together and contract their indices, and in the end I get something which is a Lorentz scalar, which has the correct transformation under Lorentz. The usual building blocks are the massless and massive spinors, which I'm not going to get into their exact definition, but all I need is their transformation under Lorentz. So if I act with the Lorentz transformation in the spinor representation on a pairwise, on a massless spinor, what I'm going to get is that the Lorentz transformation acts within the spinor on the associated momentum, but I actually get an extra little group phase, and this is what makes it a good building block for constructing the S-matrix and amplitudes. And the square bracket spinor transforms with the opposite phase. Similarly, for massive spinors, there isn't a phase here, but there's this D matrix, which is the same one that acts on the quantum states. So this is how you build an S matrix, which has the manifestly correct little group transformation. But we're missing the extra spinors that will enable us to have a pairwise little group phase. So that's what we're going to do. The little wrinkle here is that we know that the pairwise little group is a U1. So we want to have spinors associated with massless momenta. But in general, the charge in the monopole can be massive. So how do you take two massive momenta and define associated massless spinors? Well, what you do is you just do linear combinations of them. So for every pair of dyons or charge in the monopole, we take their momenta and we define null linear combinations. We call them pairwise momenta, and they'll be the associated symbol will be the flat symbol, which coincidentally, last time I gave a talk at Davis, I also had these flat variables in a completely different context of generalized unitarity. Now, in the center of mass frame of the two original momenta, the pairwise momenta are just the same as the original momenta, only instead of having an E here, I violently switched the 0th component to PC such that the reference momentum will be massless. But I can also write it as a Lorentz-invariant linear combination of the two momenta, Pi and Pj, and the coefficients are completely Lorentz-invariant. Now there's an important fact that by linearity, the same canonical Lorentz transformation that took me from the reference momenta to the finite momenta, or the massive momenta, is the one that takes the flat momenta, the pairwise momenta, to their P flats. Why is that important? Because one dictated what the pairwise little group phase is for the quantum states. And here, it also fixes the pairwise little group phase for the spinors. And of course, we want the spinors to mimic the same pairwise little group phase of the quantum states. So this is an important observation, that we actually have the correct objects. And now that we have massless momenta, the construction proceeds the normal way. We dot them with a sigma matrix, and that just ends up being an angle times a bracket spinor for these pairwise spinors. Under Lorentz, these have the correct pairwise little group phase due to the linearity of the canonical Lorentz transformation, and that means that they're the good building blocks to construct the S matrix. So now we can just take them and start constructing amplitudes. One last thing before we do this is to consider the massless limit. So the way that we constructed the pairwise momenta is such that if the mass of one of the particles goes to 0, the regular momenta approaches the pairwise momentum, and the same thing goes for the spinors. And this would actually be very important for selection rules, because we'll have in our amplitude massive spinors contracted with pairwise spinors, and when we take the massless limit, they're actually going to be parallel to each other, and it's going to vanish. So this actually tells us that there are certain non-trivial selection rules that we're going to get from our pairwise little group. We work in the all outgoing convention to be consistent with all of the other on-shell literature. And the one thing that is a little surprising already from this construction is this usual division of the S-matrix into a delta piece that's linked to forward scattering. And the amplitude is actually not pairwise little group covariant. Usually, if you didn't have this extra phase, then the delta will basically tells you that the D's are multiplied with D daggers. The D daggers are multiplied by D's. And that means that the delta itself is covariant under this transformation. But because we have an opposite sign choice for the pairwise little group for in and out states, which leads to a plus here, you can see that manifestly this delta function is not covariant under pairwise little group. So this division into a delta and an A is just not correct in the case of charge-monopole scattering. And this has a physics counterpart as well, because we know that when a fermion falls, a left-handed fermion falls into the core of a monopole, it has to come out as a right-handed fermion. Angular momentum selection rules tell you that there's no way for you to come out of the monopole core unscathed if you're specifically for the S wave. So that means that whatever you have, even if higher partial waves of the charge in the presence of the monopole pass as if they don't see the monopole at all, just from locality, the part of the plane wave that's in the S wave and goes into the monopole core has to come out different from what it started. It can't do forward scattering. And this is the physics intuition behind this absence of the delta function. Are there questions about this point? Because this is maybe the first novel result that we got here. Good. So no forward scattering. And I just have a cheat sheet. I said that we're going to use regular and pairwise spinners and kind of combine them together to satisfy the correct transformation rules of the S matrix. And this just tells us that if we postulate that we need an amplitude with overall spins SI and single particles helicities HI and pairwise helicities that are dictated by the electric and magnetic charges of the scattering particles, we can saturate these by grouping together these regular spinners, these massive spinners, and also these pairwise spinners. Finally, let me note that the results are fully non-perturbative because we're actually working black box. We're only looking at the asymptotic states, and we're only writing down, we're just writing on whatever is consistent with little group, and we're not assuming whatever is exchanged. So this is going to be fully non-perturbative. And it's similar in spirit to what you have in scattering on a central potential in quantum mechanics. Somehow you'll be able to fix the spherical harmonic part. And the dynamic part, which involves the phase shift, is something we won't be able to say a priori. So you can't, there are no free lunches. We can't like fix everything, but we can fix the angular dependence and the spherical harmonic part of the scattering. Okay, let's do a little bit of a warm up. Yeah, so I'm gonna run over this because I want to get to the gist. But okay, so let's say we have a massive fermion decaying to another massive fermion and a massive scalar, and the charges of the decay products are such that Q, which is E times G, is -1. So to account for the massive decaying fermion, we have the massive spinner here. For the one of the products, which is also massive, we have the 2 here. And because overall Q has to be -1, we're using 2 minus pairwise spinners here. And that just gives the 3-point amplitude for that process. And that is true up to just an overall constant, because there are no Mandelstam's for 3-point function. So we're completely fixing the amplitude just from regular and pairwise little group. I'll skip these examples. They're just repetitions of this exercise and demonstrating that sometimes things vanish because of selection rules. And I'll get to our main results. So using pairwise helicity, we're able to fix all all electromagnetic 3-point amplitudes. And I'll go over just one of them, the 3-point amplitude for 3 massive particles. So from Nima's paper about massive amplitudes for all masses and spins, we know that if we have the 3-point amplitude for spin S1, spin S2, and spin S3, what we need to do is have 2s insertions of the massive spinner for 1, 2s2 insertions for 2, and 2s3 for 3. And somehow their indices have to be contracted with one another. Now, in Nima's case, he didn't consider magnetic scattering, so there was no net pairwise helicity in his case. So the only way to contract these indices was either with the epsilon tensor or with bilinears from by momentum bilinears, which are overall little group neutral. In our case, we have an extra transformation rule that we have to satisfy, so we have to contract these indices with the right number of pairwise spinners that saturate the transformation rule. And there's a way to write the most generic thing that you can get. So you take a minus spinner, which we call W, and a plus spinner, which we call R, and you have just the right amount of them to have a net pairwise helicity of minus Q. And now you sum over all this symmetrized way of contracting them with the massive spinner. And that's it. That's the amplitude. It also gives us a selection rule because you can't have a negative number of insertions of the minus spinner. So in particular, it tells you that the pairwise helicity absolute value has to be smaller than the sum over the spins of all the particles. So this is a selection rule that you just get from pairwise helicity. In particular, it tells us that if I have 3 massive scalars, so S hat is 0, Q absolute value has to be 0 as well, which means that I can do a duality transformation on my dyons to take them all simultaneously to charges. So basically, they're just like, it's just a charge decaying to 2 other charges disguised as dyons by an overall duality transformation. Similarly, I can work out other cases, a massive particle decaying to an incoming massive particle decaying to an outgoing massive particle and a massless particle in the unequal mass case, in the equal mass case, and I get other selection rules, which I'm not going to go into too much because I want to get to 2-to-2 scattering. But just for reference, I'm going to have the slides up later, and you can look at these selection rules. And they generalize the selection rules that Nima has in his paper for non-magnetic scattering. Okay, so let's get to 2-to-2 scattering. And here, in spirit, what we're doing is we're fixing the spherical harmonics, or the monopole spherical harmonics of the scattering for each partial wave of this 2-to-2 scattering. And I'll show how to do this. Okay, so what we do is there's a way to do a fully relativistic partial wave decomposition for 2-to-2 scattering. What you do is you define the quadratic Casimir of the Poincaré group, W squared, which is just the square of the Pauli-Lobonsky operator. and you can act with that operator on amplitudes. So the amplitude will in general be a sum of eigenstates of this operator. Each eigenstate will have its own eigenvalue, and the j here in the eigenvalue is literally the angular momentum of the partial wave. So this is just the partial wave decomposition. And I will show how to do this in a completely pairwise little group covariant way, such that each particle, each term in this expansion respects pairwise little group individually, and that will force the angular dependence of each term separately to be what's called a monopole spherical harmonic. So now I'll just show in equations what I said by words. We split the S-matrix into a sum of eigenstates of this quadratic Casimir operator. This is just the formal definition of what this operator is. So it's a sum over eigenstates of this W squared with coefficients that are dynamical. They're equivalent to the phase shifts that we have in quantum mechanics, which depend on the shape of the potential, so we can't know them a priori, times this part, which is the actual eigenstate of the angular momentum operator. So that's morally like a spherical harmonic, and we'll show how to completely fix it. So what can this eigenstate be? It's some contraction of regular and pairwise spinors, such that when I act with the quadratic Casimir associated with particles 1 and 2, when I measure the angular momentum of the incoming particle 1 and 2, I get a particular eigenvalue. Now I know that the eigenstates of the angular momentum for particle 1 and 2 are just combinations of spinors in which all the indices are undotted, and they're also symmetrized. They're symmetrized, it's kind of along the lines of Young tableau. This is what says that they have to be symmetrized. And also the number of them is like the number of boxes in a Young diagram. So there are actually 2 J spinor indices here. So there's one coefficient that's associated with the in state and another coefficient which is associated with the out state. And the fact that there's the same number of indices here and here just reflects the fact that the overall amplitude is a Lorentz scalar. So all spinor indices have to be contracted. The J of the incoming state is equal to the J of the outgoing state. So I know how many spinor indices I have. Another question is, how can I fix this coefficient? Well, I have another tool in my arsenal, and it's the pairwise little group that we were talking about. So each one of these parts has to be a combination of spinors that has the right transformation rule under pairwise helicity. And the way to get them is somewhat of a trick. I can write down an temporary imaginary amplitude for the 2 in-state particles going into a fictitious mediator, a massive particle of spin j. Now, I already told you that we derived all the 3-point amplitudes, so we can easily define the pairwise little group covariant amplitude for the 2 in-state particles going into a spin j. And now we just peel off the massive spinors for this fictitious mediator j to get 2j free spinor indices. And this is how we get exactly the object that we need. We have the right amount of Lorentz indices, and we have the right pairwise helicity transformation. And we can always do this. For example, let's look at charge-monopole scattering. So in this case, the monopole is a scalar. The incoming charge is a fermion. So the overall S is 1/2 plus 0 plus j of this fictitious mediator. And by the selection rule that we saw earlier, that has to be larger or equal to Q absolute value. It immediately tells us that the lowest j in our angular momentum expansion can only be absolute value Q minus 1/2, something that we didn't know a priori. And this is something that Kazama, Young, and Goldhaber found explicitly by solving the Dirac equation in a monopole background. And we just get it from our selection rule for free. Moreover, we don't just have a selection rule, we have a way of constructing all these 3-point amplitudes. So we can write this C coefficient for the in state, this C coefficient for the out state, and just dot them together and literally get the angular dependence, or the part of the amplitude which is an angular momentum eigenstate for the lowest partial wave. And this is what it is. And interestingly, the answer is different if Q is positive or negative. The interesting thing is now we can take the massless limit and get very surprising results. We take the massless limit by unbolding the massive spinors here. And we use the fact that, like we said earlier, the regular spinors and the pairwise spinors tend to align with each other in the massless limit. So if we're not careful, we're going to have things that will vanish in the massless limit. And indeed, that's the case. By carefully taking the massless limit, we see that for negative Q, the only non-zero amplitude is if the incoming fermion is right-handed and the outgoing fermion is left-handed. So we have to have a helicity flip in the lowest partial wave. For positive Q, the only non-vanishing amplitude is a left-handed fermion going into the monopole, which then turns to a right-handed fermion, which comes out. So again, this is a very surprising selection rule. It means that there's no forward scattering in the S wave. Other people derived it decades ago based on full solutions of the Dirac equation, and we just get it from our pairwise helicity selection rules. And we also substitute the explicit values of the spinors and see that we numerically reproduce the quantum mechanics result. Moreover, I told you that we can fix the angular dependence for each partial wave, but we don't necessarily know what the phase shifts are, what the relative coefficient of the different partial waves is. However, in the case of the lowest partial wave, we have this selection rule that a left-handed has to go to a right-handed, and a right-handed has to go to a left-handed. And it's 100% of the probability. So that's essentially telling us that our phase shifts are exactly one, and this reproduces the quantum mechanics result. So at the lowest partial wave, we don't even have the unknown of the phase shift. We can fix it completely together with the angular dependence. For higher partial waves, we don't have this privilege, so we can only reproduce the angular part and not the phase shift. But interestingly here, the stars is kind of a line. We sum over all the different possible contractions of the C coefficient that we can write for the in state and for the out state. And when you do this, the sum correctly, you find that everything telescopes into just a Wigner D function. So what we did is we used pairwise helicity to write down the generalization of the Jacob-Wick formula for charge-monopole scattering. It's the pairwise helicity modified Jacob-Wick formula. And this is what it looks like. The regular Jacob-Wick would be if I set Q here to 0. And now we see that the only modification due to this pairwise helicity between the monopole and the charge is to modify and insert Q and minus Q here. And a priori, we don't know what these phase shifts are for the higher partial waves, but we can just extract them from the non-relativistic quantum mechanics result of Kazama, Young, and Goldhaber. And finally, these D matrices are just related to what's called monopole spherical harmonics. So it's pretty satisfying to see that we derived them in a completely on-shell way. Good, so let me conclude. We solved the problem of constructing Lorentz covariant electric magnetic amplitudes. We identified electromagnetic multi-particle states are not direct products because they have this extra phase associated with each pair of particles in the amplitude. We define the pairwise little group, the pairwise helicity, and also spinor-helicity variables, which are building blocks for amplitudes. And using them, we fixed all 3-point amplitudes and the angular dependence for all partial waves in 2-to-2 scattering, including the non-trivial helicity flip for the lowest partial waves. And then there are many more applications to come. Thank you.
Hey, questions? This is the part where you're supposed to talk, Marcus.
Well, I mean, yeah, I had some questions. I think I'd like to have some fuller explanations of some of the things that you talked about, but I sort of think that maybe we should, you know, maybe other people, I feel like I already took up a lot of time during the talk, so I just wanted to give somebody else a chance and maybe ask that after in the informal part. So.
What applications are you thinking about?
Did you hear the question?
No.
Sincha said, what are the other applications you're thinking about?
Oh, yeah. Yeah, good question. So let's see. Let's see if I can remember all of them. So it's monopoles plus X, and insert in X every part of modern physics that you'd like. So monopoles plus SUSY. So I actually have a draft that I wrote, which is, it's still halfway through, but basically doing this in the context of dyons in n equals 4 super Yang mills. And I want to see if I can indirectly infer several things. For example, if I can say something about walls of marginal stability using scattering and pairwise helicity, or if I can reproduce the formula that basically the BPS bounds, that somehow the mass of the state is related to the electric and magnetic charges, which is something you can see semi-classically right away by solving the analog of a Toth-Polyakov monopole, for example. But I want to see if you can get it from a purely on-shell point of view, which is automatically valid in the quantum regime as well. So that's one thing. Also, one thing we're thinking about is what happens if you have more dimensions? So there are two paths. So like John mentioned earlier, let's say D is not 4, it's something larger, but you still insist that you're scattering point particles in that higher dimensional space. In this case, the pairwise little group would actually generalize to a larger group, and there will be also triplet little groups and little groups of more particles. But in this case, I'm not sure what the physics interpretation or the physics meaning of that Hilbert space construction is. However, you can follow a different path and you can say, let's stick with the fact that these are charges in monopoles. Well, we know that for higher dimensions, the sources of electric and magnetic fields are actually branes, and are branes that are Poincaré dual to one another. So if you take that into account and you repeat the pairwise little group exercise for the momenta transverse to the branes, you see that you still maintain that the pairwise little group is a U1 for these extended electromagnetic sources in the higher dimension. And that actually makes a lot of sense because we know that there's Dirac quantization for branes. So somehow this should always be a U1 with an associated helicity. And indeed, that is the case. Other things that we're thinking about are we're thinking about using these pairwise variables to actually characterize and expand non-magnetic amplitudes as well. And then, John, is there anything that I forgot?
The original reason for starting all this was Rubikov-Kalin.
Oh, right. Yeah. So, so I think, yeah, we should. So the thing about Rubikov-Kalin is no longer 2-to-2 scattering. So we should work out explicitly the case of scattering of more particles.
And there's some analogous statement about instantons and strings in 4D, at least formally.
Right, because they have also like an analog of Dirac quantization, I would say. Yeah, and then last but not least, I think we're trying to scout if there's any connection between the pairwise little group phase and the Aharonov-Bohm phase. And we think that there should be some connection between like the overall Aharonov-Bohm phase that the charge accumulates as it scatters off the monopole and the angular dependence of our monopole amplitudes.
And then there's the connection, the classical double copy and with magnetic charges.
Oh, right. I forgot about that. Yeah. So so we're getting pretty. So this is something I'm working on with Donald O'Connell and others. Maybe actually tomorrow, maybe Yutin Wang will join us. I was working out the double copy between monopole scattering and Taubnut space, which is something that they did perturbatively, but without pairwise helicity. So their results were only valid in a very limited range, basically in the iconal or classical limit. And we're extending it to the full quantum result because this is the full quantum result. And we're seeing that the same monopole spherical harmonics that we have here arise for the Taubnut space as well.
Are there any other questions? Okay, then we're gonna take things private.
Awesome. Thanks
So
for
let's
having me.
thank Ofri again.